here and get Clark here. Okay. Oh, yuck. Doing well. Okay, we are recording. We'll go from current slide. And maybe you can turn on the projector. And let me go over just a couple of announcements. None of these too major. First, you know about the Alabama A&M North Scholarship Program. Okay. Now, there may be some others like that. I haven't been able to check emails much lately, except just taking care of whatever the emergency of the hour was. But let's just let you know a few changes to my schedule. On Fridays, I'm usually on the Birmingham campus, 8 to 12. Did I tell you this last time?
Yes.
Oh, I did. Okay. This Friday, I've got a dermatology appointment, 9:15, which is right in the middle of the morning, so unfortunately, but it's the only time I could get, or the only time they gave me anyway. I don't know what was available. And so I don't know if I'll be there before the appointment, but if so, it'll only be 45 minutes or so. But after the appointment's over, I plan to go to the campus then. Probably not for very long, at least an hour or so. All right, maybe, but certainly longer if possible. All right, the following Friday, though, not in town at all. I'll be driving to Mobile. I'll probably leave home about 7-ish in the morning, driving to Mobile. I think we talked about it was 4 to 5 hours, I'm guessing.
Yes.
And then be there for 3 hours and then drive back for 4 to 5 hours. So it seems like a waste of day, but I guess I'll be doing it. So that's the next Friday. The following Friday after that, I've got an eye appointment. But that'll be right across the road here at UAB West. And so I'll probably just come back here and spend the rest of that Friday here, unless there's a need for me to go to the Birmingham campus. And I can easily go there. Hopefully I can easily go there because I don't like doing too much with the eyes messed up, you know. But anyway, that's those things. And then sometime in there is spring break, okay? It comes at the end of the month. All right. Let's, I think right before class we talked about Emmy Noether, woman who was sort of helped Einstein when he got stuck in math. Okay, pretty sharp chick here, you know. And it talks here about our knowledge of axiomatic systems, which we won't even go into, generally recognized as the leading woman mathematician in recent history. A sharp dude. But the sad news was she died on the operating table for some really simple operation like appendicitis or something. And something just went woefully wrong. I don't know what it was. All right, but anyway, that was her picture. Here are the properties of vector operations. We've already talked about some of these. This just formalizes the list, so to speak. So here we have, I didn't ask, any questions before we get started? Okay. U, V, and W are vectors in the plane. Okay. When they say in the plane, 2 dimensions. That's what in the plane means. We're in 2 dimensions. So these, I think, all apply to whatever dimension you were in, but they certainly apply to 2 dimensions. And let C and D be scalars. And the reason they keep saying in the plane, the title of this chapter is Vectors in the Plane. Or this section is Vectors in the Plane. It's vectors in geometry of space. We're going to get out of the plane soon onto the tarmac. No. Okay. C and D are scalars, just plain old numbers with no direction associated. Now, we talked about this before, the commutative property of addition, and I would put of addition there too, rather than just commutative property. But u plus v is the same as v plus u. Doesn't matter what order you add vectors. Subtracting, yeah, that would make a difference. But adding, no. U plus v plus w is the same as u plus w, v plus w, or w plus v too. That's the associative property of addition. Okay? I would say of addition of vectors, in fact. Number 3, u plus the 0 vector is always u. Okay, the 0 vector, of course, the vector with both components being 0. So that'd be u1 plus 0 is u1, u2 plus 0 is u2, u1, u2 is u. Okay, or u, whatever. That's the additive identity element. Okay, additive identity property. U plus the negative of u is the 0 vector. That's basically subtracting this, adding that, same deal. Okay, so that's the inverse addition, additive inverse property. That's what it is, additive inverse property. Now, this is where things get a little shakier. The addition, not bad at all. When you start multiplying, you have to be a little more careful. There is sort of an associative property of multiplication, but it's only when you've got two scalars, okay? C times du is the same as CD times u. So you can associate, if you've got two scalars and a vector, it doesn't matter how you associate the scalars. You can multiply, okay, that's fine. Now, distributive law property, also you have to be careful. Two scalars, the sum of two scalars times the vector is the sum of the scalar times the first vector plus the scalar. First scalar times the vector plus the second scalar times the vector. That's a form of the distributive property. Another form, if you have two vectors and one scalar, and you're adding the two vectors together, then that's also c times the sum of u plus v is c times u plus c times v. Sorry, the sum of the products. And then this one, 1 times u, of course, is u, and 0 times u is 0. Okay, this is the multiplicative identity element, and this is just multiplying by 0. Okay. Now notice this 0 is the scalar, and this 0 is the vector 0. Okay. Not a lot of difference between them, except I was going to say the 0 vector has direction, but it doesn't have any direction, so not a lot of difference, except that is a vector, meaning it has two components. This is a number, just one. Okay. I guess that's all you can say. Now, they do a proof here, and most of these proofs you can do just like this one. Split the vectors into their components and deal with that. Because then you're dealing with numbers, and you know these rules for the numbers. Okay. Now, let's see if this next thing, yeah. Any set of vectors with an accompanying set of scalars that satisfies the 8 properties that were just listed in Theorem 11.1 is said to be a vector space. Okay? If you had done, and I think some of the others are doing linear algebra, we're going to get into vector spaces. The 8 properties of the vector space are the vector space axioms, and this is where Emmy Noether came in. She was axiomatic, rules and stuff. Excuse me. So this theorem states that the set of vectors in the plane with a set of real numbers forms a vector space. All right? That's what the previous one did. They made it seem like this one. This theorem is just saying something else. The length of a scalar multiple. That should have been on the last slide. This should have been somewhere else. Okay. If V is a vector and C is a scalar, then the magnitude of C times V is simply, now remember magnitudes are always positive. So you can't just pull out the C and have it out here because that C could be negative. So you have to do the absolute value of C times the magnitude of
And the magnitude is the length.
Yeah, magnitude of a vector is the length. So if you had a scalar times a vector, you increased or decreased its length depending on the size of C. And the magnitude or length of that vector would be the magnitude of C, meaning absolute value of C, times the magnitude of the vector V, the original vector. Okay. All right. A few other vector operations. Many applications of vectors, it's useful to find a unit vector that has the same direction as the given vector, but only magnitude of 1. This next theorem gives a procedure for doing this. The unit vector in the direction of V. If V is a non-zero vector, okay, guess what? You can't make a unit vector out of the zero vector, okay? You can't do it, there's no way. So V has to be a non-zero vector. In the plane, we're saying in the plane now, then here's the vector U, which will be the unit vector in the same direction of V, but 1 unit of length. Always 1 unit of length. Take the vector V and divide by its magnitude. Because vector V is a vector of length magnitude of V, to get it of length magnitude of 1, divide by the magnitude. Okay? Or the other way to express it is 1 over the magnitude times the vector V. Has length 1, same direction as V. In this theorem, U is called the unit vector in the direction of V, clever name for it. The process, that's why they gave it the title here, okay. The process for multiplying V by 1 over magnitude of V to get a unit vector is called the normalization of V. Now, that is a word, especially in mathematics, that I find almost a bit overused. Sort of anal retentive, I think, not being studied. Okay? When you talk about a normal vector, which we will in subsequent things, basically that means perpendicular. And normal quite often means perpendicular. Okay?
Perpendicular
to something else.
Oh.
Yeah. We'll talk about soon a tangent vector. Okay? That makes sense, right? The normal vector is a vector perpendicular to the tangent vector. And that points in the direction of the center of curvature. Whatever your curve is doing here, the tangent vector, normal vector would be directly toward the center of that part of the curvature. Okay. And then there's another one called a binormal vector that's perpendicular to both of those. That's when we get in the 3 space. I'm not going to do that. So quite often normal means perpendicular. Okay? But here it means making it of length 1. And that's a very common use of the word normalize too. In fact, it's used sort of in everyday speech. Well, let's normalize the data, meaning let's get it all on the same scale type thing, in reference to some unit vector, you might say, of magnitude 1. All right. Generally, the length of the sum of 2 vectors is not equal to the sum of their lengths. Okay? Generally, the length of the sum of 2 vectors is not equal to the sum of their lengths. And here's why. Huh?
I think we skipped an example.
Oh, we did. Sorry. Glad you caught that. I would have picked it up later. Yeah, example 4. So they skipped it, and I was just merrily going on my way of skipping it. So, wait. Okay, let's do it here. Example 4. Finding a unit vector. Good catch. Find the unit vector in the direction of V. Oh, let me get my pen set up. Okay. I just happened to realize one reason, if I'm sounding sort of nasally today, and I know I've been clearing my throat a lot, I do this frequently. I like as a salad dressing, a barbecue sauce. I mean, it just has a lot more flavor to me. And so quite often when we have barbecue or something and it comes with sauce, if there's any left over, I use that as my dressing for my salad when I bring it to lunch. Well, we went to a new place last weekend. It just has opened. Goodness gracious, I can't think. I want to say Robert Smith. That doesn't sound right. But anyway, it's a new barbecue place fairly close to where we live. Not the closest one, but fairly close. And he's won all sorts of awards. He's from Charleston, South Carolina. So it's a different kind of barbecue sauce. Yeah.
Sort of the sweet heat.
Huh?
Sort of the sweet heat from the Carolina. Sweet heat.
Sweet teeth?
No, sweet heat.
Sweet tea.
That's right.
Okay.
Sweet heat. Heat. Like hot.
Oh, sweet heat. Okay, got what you mean.
Right.
Okay, that's exactly where I'm heading right now, especially the heat part. We got, he said sauce with the barbecue, and I think my wife probably ate more of the barbecue than I did. I was eating some other things too, and we had some barbecue left over from earlier, so I was trying to eat the old stuff. So I hadn't had that much of his sauce, and when I had it, it was just on the barbecue, and it sort of absorbed it pretty well. When I put it on my salad for lunch today, it loosened the sinuses like crazy. I have been draining ever since, so that's why I'm sounding and having to clear my throat because it's going to it. So sorry about that.
That is a good idea, though. I never have thought about putting barbecue sauce on the salad.
Yeah, well, I don't know if you've ever been to Jim and Nick's. They have the pig in the garden salad, and that's where I started doing it. They said, well, what do you want as a dressing? I thought, well, don't have the barbecue on the salad. I just as soon have the barbecue sauce on the barbecue and let that be my dressing for the salad too. And I liked it so much that even if I don't have the barbecue, I still do that. But boy, this one, yeah, Scott, Rodney Scott's, that's the name of this new place. And it's good. Rodney Scott's Whole Hog Barbecue.
Where is it?
Well, it's brand new in town. Are you familiar with Southside Birmingham? Okay, Forest Park area, kind of. Well, you know where the new Avondale part is. Okay, we live fairly close to that. Okay, if you go up, let me think which street it is. 2nd Avenue, maybe? Going toward UAB from Avondale. Just right there in the middle of not much of anything. There was a place called Saigon Noodle Bowl or Noodle House or something like that. Okay, they closed and Rodney Scott's in their place.
Oh, okay.
Yeah, so you know where it is,
Yes,
but yeah, it's good barbecue. It really is. I see why he's won awards. Okay, enough paid political advertisement here. Okay, let's do example 4. Find a unit vector in the direction of V. Vector V, I can't do bold, so I put a little arrow over it, equal to angle bracket -2, 5. Okay? And verify that it has a length of 1. So what would be the unit vector, let's name it U, in the direction of V. So I'm going to put a sub V down here so you know it's a unit vector in the direction. In fact, here's something else I do. The book doesn't do it, but I do it. If I'm doing a unit vector and it's a unit vector, I like to put the caret hat on it. That indicates to me that's a unit vector. Quite often there's UVW, just like up here. They didn't use a U, but they could use UV and W, and U could be any old vector. If it's a unit vector, I put a cap on it. Okay? It's something I don't know if you've seen this. The IJK vectors. Have you ever seen them represented that way? Okay, well, sometimes they are. That hat means they're unit vectors. Okay, but I use it for this too. So what would be the unit vector in the direction of V?
I'm sort of
What's that?
I don't really understand like on the last one,
Mm-hmm.
it said U equals V over
V over
V.
magnitude of V. You're absolutely right. That's it. Well, V is simply negative 2, 5. That's the vector V, right? Over, and what's the magnitude of that vector V? The magnitude is the same as the distance.
So you're
Okay. I gave a visual hint there.
Oh. Well, is it the square root of 29?
The what?
Square root of 29?
You got it. Negative 2 squared plus 5 squared. Absolutely right. Which is vector 2, 5 divided by the square root of 29. Square root of negative 2 squared is 4 plus 5 squared is 25. That would be 29. So you could write this just as a vector, minus 2 over root 29, comma 5 over root 29. Root 29 leaves Athens, Georgia, and goes to Atlanta. No, okay. All right. So that's how you could leave it like this, but that's probably how they were looking for it. Now, the second part says, verify that it has a length of what? Well, length is magnitude. So what we'll do, the magnitude of this then would be the square root of negative 2 root over root 29 squared plus 5 over root 29 squared. Okay? That would be the square root of. When you square negative 2, you get 4, and square root 29, you get 29, plus square 5, you get 25 over 29, and you get the square root of 29 over 29, 1.
And how do we know to take the square root of those two things?
That's what you do. It says verify that it has a length of what? Well, length is the same as magnitude or distance. You know, all those terms meaning pretty close to the same thing. The reason I said distance before is I was trying to get distance formula into your head. And since you came up with it, I felt like maybe I succeeded a little bit. Okay. All right. Got it?
Yes, sir.
Okay. Now, that was example 4. Now I think we're ready to move to the next slide. If I can find there. There we go. No, that's not it. Not that. This one. Generally, there it is. Yeah. The length of the sum of two vectors is not equal to the sum of their lengths. Okay? And here's sort of a, to me, straightforward reasoning on that. The only time they are the same sum of the two lengths, or if they're in the same direction. If you have vector 1 added to vector 2, and they're in the same direction, then the magnitude of that is going to be equal to their length. Can never exceed, okay? The sum of two vectors can never exceed the sum of their lengths, okay? But if either of these vectors is at any angle, then it's just gotten shorter. The sum has gotten shorter in length. So it can never, generally the length of the sum of two vectors is not equal to the sum of their lengths. It can be exactly equal to, never can exceed. To see this, consider the vectors u, v as shown here. And this gives us what they call the triangle inequality. That u plus v, vector u plus vector v is always greater than or equal to the sum vector u plus Okay? Now, a better way of expressing that is this one. We're talking about links anyway. In fact, what I said was probably sort of meaningless because adding two vectors, you get a vector. So it's hard to say one vector is. Here's how you best say it. The links are, the length of u plus v is always less than or equal to, it can be equal to, the length of u plus the length of v. Only time that equality holds if u and v are in the same direction. Okay? Identical, straight line. Okay? Equality occurs only when vectors u and v have the same direction. That result is called the triangle inequality for vectors. Okay? The magnitude of the sum is less than or equal to the sum of the magnitudes. That's one way of expressing it. All right. Okay, that didn't have a problem with it, so excuse me. Let's move on to standard unit vectors. I just mentioned them, or at least three of them. These are two. The unit vectors 1, 0 and 0, 1 are called the standard unit vectors in the plane and are denoted by I and J. Okay? I being 1, 0, that's the one in the direction of the x-axis. J being 0, 1, the direction 1 in the direction of the positive y-axis. Those are your standard unit vectors in the plane. Okay? Now, these vectors can be used to represent any vector uniquely this way. In fact, oh, here's Daniel. We doubled the class size. Okay. Daniel did it for us. Okay. All right. This is kind of doing backwards from what I've often done in the past, or how I learned it. Back when I was growing up, I'd never seen this notation for a vector, the angle bracket. I just don't ever remember seeing that. Maybe it was there and I just don't remember it. Okay? But you probably wouldn't have thought of doing this, but it's certainly true. If you break this vector v, v1, v2, into the sum of two vectors, the first vector being vector v1, 0, and the second vector being 0, v2, yeah, when you add those together, add these two components, you get v1, these two components, you get v2. Yeah, that gets you right back there, all right? Well, this is exactly whatever v1 is times 1, 0, okay? And this is exactly v2 times 0, 1, okay? So, another way of saying that is v1i, because that's the I vector, plus v2j, that's the j vector. Now, when I was growing up, this was what we called component form of the vector. You wrote them this way. v1i plus v2j is the vector v. Now we call this a component form and say, hey, look, this is just using these this way. Whereas before, this was what I considered the component form. So I will sometimes use those interchangeably just because that's what I'm used to. The vector v is vii, and v1i plus v2j. Now here is where I would be putting caps on this. It's called a linear combination of I and j, which is exactly what that is right there, and that is also. The scalars, v1 and v2, they're just scalars. They're the components of a vector. They're called the horizontal and the vertical components of vector v. And especially when you get to physics, you're in physics already, aren't you, Dave? Yeah. And yeah, this is what you use a lot, horizontal components and vertical components. Now, sometimes, especially, say, an object on a plane, okay, what you're interested in is the things that are parallel to the plane and perpendicular to the plane, which also is called normal to the plane. So then sometimes this would be, V1 would be the parallel component, and V2 would be the perpendicular component. And you do talk about things that way too. But this is talking more horizontal and vertical that way. What you do with the plane, you move your axis to go up and down the plane, but you have to twist a button. So they're no longer horizontal or vertical. All right. Here's example 5, which is the next one in the text, so we'll do it this way. Let U be a vector with the initial point 2, -5. How do you know that's a point? That looks a lot like a vector, doesn't it? How do you know it's a point?
Oh, yeah.
The parentheses. Terminal point, and they tell you it's a point 2, -1, 3. Okay? So there's your vector U. Okay? So vector with initial point 2, -5, terminal point -1, 3. Let vector V, on the other hand, be 2I minus j. Write each vector as a linear combination of I and j. My word, I think they just did it for V, didn't they? Oh, each of these two. Okay, got it. I was going to say, wait a minute, that isn't it, but they're saying these two vectors here. So what's U as a linear component of I and j? Just like V is written as a linear component of I and j there. This isn't a one-step deal. You're going to have to take a couple steps here.
So, go back to U equals V over the magnitude V.
No, you don't need that here. I don't think that would be at all helpful. You go way back to going from a vector in the form of PQ to writing that in component form, where P is this point and Q is that point. Remember when we did that? That was quite a bit further back. Well, here's the hint. Always think terminal minus initial, final minus initial. That's always the differences here. Yeah.
Okay, so now we need 3 minus -5.
Second?
3 minus -5.
Yes, that was the y part. So 3 minus negative. Goodness, I can't write. Let me try that again. You're giving there the y component, which is 3 minus a minus 5. What's the x component? And I shouldn't be putting parentheses here. Should be putting vector brackets. What's the x component?
-1 minus 2.
-1 minus 2. So this would come out being -3, comma 8. Perfect. Okay? But that's just getting it in vector notation. We want it in linear combination of I and j. So this would be what? In other words, so it looks like the V up here.
Vector 3, comma 8 equals -3i.
Right. Plus
8j.
8j. See, that's where I put my carrot hats or dunce hats or whatever you call it. So that's U in, now my nose is itching, linear combination of I and j. Now we're going to do, now that we've got that, we can do W. And since you're going to have to get it in that form anyway, why don't we write it in that form? W, vector W, is equal to 2 times, and this would be -3i plus 8j. j minus 3 times, and your v was 2I minus j. So this
the last part, is that a plus because A is positive? Because
is it what?
On the last part, the 3I plus 8j, is that a plus because 8 is positive? Because in the top one, it's got the V equals 2I minus j.
Okay. This is that. You're mentioning that. The reason I put the minus 3 here is this.
Well, no, sir, I was talking about where it's the plus 8, 3I plus 8j.
Right, this up here?
Yes.
That's a minus 3I, right?
Mm-hmm.
Okay. So that's what you start with here. 2 times, this is vector u. This thing right here is vector u. So 2 times the vector u, and this is what w is. 2 times the vector u, which will be minus 3I plus 8j, minus 3 times the vector v, which is that one there. Is that what you meant?
Well, I was just asking, why is it plus 8 and not, because it, I mean, I was thinking that where it says v equals 2I minus j, I thought that was like a standard form or something, so I was just wondering why it's plus. And was that because 8 is positive?
Yeah, because 8 is positive, yeah. It's just whatever your coefficient is. And let's make sure we got that right. It's 3 minus a minus 5, that is a positive 8. The other one, negative, just because it added to be a negative number. So yeah, there's no standard form. It's usually AI plus BJ. Usually plus would be the standard form, but it just happens to be your coefficient there is negative, so it would be a negative J. I realize that a lot of what they've done so far have always been negative there, but it doesn't have to be. It could be plus or minus. So does that answer it or not?
Yes, sir.
Okay.
Yes, sir.
So where do we go from here? Basically, distribute. Remember, we had that earlier.
Yes, sir, I was just writing my-
Oh, okay, right. What does this come up being?
I'm trying to figure out what those squiggly lines are.
This? That's not a squiggly line. That's a caret. It's a housetop. It's a. That's what I use to indicate a unit vector. Rather than just doing a bold and you can't tell if it's unit or not. Those are unit vectors. What's that? Okay. It's just my symbology for a unit vector. I'm not the only one. Other people use it too, but I like to use it because it reminds me this is a unit vector. You can't recognize what?
Yeah, I couldn't recognize them as letters at first because, like, I'm seeing two examples, but they don't look like each other, so I thought they were something different for a second.
You mean the carets or the letters underneath the carets? The letters, that's an I, that's a J. Your standard unit vectors are I and J. Well, if I were printing, I guess I would do it just like that, but usually a little cursive in it.
Yeah, I thought that was a U at first.
Okay. It's not. I've been.
I keep seeing I up there, but there's a U right there, so.
This is a U.
Yeah, I know. It's just that
Okay.
I thought they were U's, so I was
Okay.
confused. So.
Okay. Well, I do curve the I most of the time just because I'm used to writing it that way. But if it's a unit vector and it's written in this form, that's usually I and J. Okay, and these are unit vectors written in that form. So what would you do with that? Say again?
We distribute
Yeah, and what does that give you?
negative 6I
Yeah, negative 6I
plus 16j
16J
minus 6I plus 2J.
And then what could you do from there?
I guess ties. You combine.
Yeah, combine like vectors, okay? So this will be negative 12I plus 19J. All right, let's see if that's what they got. Negative 12I plus 19J, and earlier they got minus 3I plus 8J. Good deal. Okay. Let's see how they did it.
And so your J and your K are pretty much like it's sort of saying like where you're positioned.
Say that one more time.
I said your J and your K are pretty much taking the place of your X and Y. Right?
Yeah, yeah. Or I and J.
Position.
Yeah, I and J. Yeah, right. The K takes the place of Z. Yeah. It indicates the unit vector in the Z direction, and I is the unit vector in the X direction, and J is the unit vector in the Y direction. Yeah.
And so that's like negative 12X.
Right.
Down into negative, and then
exactly.
up 19, and that's
Right, exactly. Right.
And that's starting from like 0 to 0.
Yeah, exactly. So if I were at the origin here, these are positive X's and positive Y's and positive Z's. This would be a minus 12I. That would be out front of the building, 12 units that way, plus 19J. That would be this way, 19J here. Well, that would be some vector sort of like that. Well, it's on the floor, so it would be down there on the floor between that and this, and closer to this because the 19 wins over the 12, so that would be the direction. So if I want to translate that back to your quarter, it would be coming out sort of about where your foot is, maybe the second foot. Okay. Oh, man. All right, let's see how they did it, which I think will be fairly close to similar. Okay. Solution. Oh, yeah. They went back to QP like I did, but they didn't list it, but they broken it down into the components. Point P being 2, negative 5, point Q being negative 1, 3. So your U vector would be the Q1 minus P1, comma Q2 minus P2. Excuse me. Gracious. Oh, almost dizzy. All right, so that would be negative 1, 2, minus 3, or 3 minus or minus 5, just like we did. And that gave you a negative 3, 8. Or, to write it in vector, I was going to call it vector's component notation, but, this book is calling it the, what do they call it? What I used to call component notation, they call it linear combination of I and J. But I called it component notation when I was growing up, because that was component notation when I was growing up. Okay. And then if you do W to be, a sum of multiples of those, it's 2 times that plus minus a 3 times that. So that gave us, it's just like you did in yours, minus 12I plus 19J. Okay. I am afraid I'm going to have to take a little break here. I thought I wouldn't, but I do need to do something. This has been a totally weird day. I saw it, but it's seems to have stabilized a bit. All right. Yeah, we finished that one. All right. Let's get back to standard unit vectors. I'm trying to find this slide, I think. Okay, they're skipping example 6, so let's go back and do example 6. I was thinking this is confusing here. Okay, here's example 6. Seems like they needed to have some of this verbiage here before they did example 6. And they've left it out completely. So here, I'm going to try to fill in the gap here. Why it's not on the PowerPoint, I don't know. We've got U being a unit vector, so I'm going to indicate that by the caret on top. So U is a unit vector. And theta is the angle measured counterclockwise from the positive x-axis, just like we're used to doing in trig, right? That's the angle theta. Counterclockwise from the positive x-axis, okay? And this could be in any quadrant, by the way. I just drew it in the first quadrant, but you could carry it on around to here, you know, into fourth quadrant. Then this would be theta, you know, whatever. So theta is that angle measured counterclockwise from the positive x-axis to the vector u. So this would be the vector u then. The unit vector u, okay, with Metz being here. Okay. Now, then the terminal point of u lies on the unit circle. Remember they said u was a unit vector, so let's just imagine these vectors are the same length here, okay? Then this would be the unit circle, okay? Okay, that would be the unit circle because the magnitude is 1. Then you would have the vector u could be represented by, if you think about this, break this down into vertical component and horizontal component, right? And the magnitude here is 1, okay? The magnitude is 1. Then, the y component on the unit circle, the magnitude that was the component for, that was what sine x is. Remember that? Because if this is, well, let's call it theta, because I wrote it as theta. Theta is, the sine of theta is opposite over hypotenuse, right? And the hypotenuse is 1 on the unit circle, right? So therefore, this is just sine. This is sine theta. Sine theta is this over that, so that's over 1, so it would just be your y component. Cosine theta would be the x component, okay? Because it's adjacent over 1. So therefore, in component form, this is cosine theta, that's the x coordinate, and sine theta is the y coordinate, okay? So that vector, unit vector u, written this way with that angle theta, is always going to have those components. If it's a unit vector, magnitude is 1, and we know that's true, right? Because cosine squared plus sine squared is always 1. Okay, so the magnitude is definitely 1. Okay? Now, written in the other notation, linear combination type thing, this would be cosine theta I plus sine theta j. Okay? All right. Moreover, it follows that any non-zero vector v making an angle theta with the positive x-axis has that same direction as u, if it has the same angle, and you can write v then, any old vector v, doesn't have to be a unit vector, as the magnitude of v cosine theta, did they put I? Yes. Okay. I plus magnitude of v times the sine theta j. Which, if you wanted to, just factor out. I don't know why they didn't, but they didn't. I won't do it either. Well, they did it backwards. Okay. Magnitude of V times cosine theta I plus sine theta j. Or the other way of writing that is the magnitude of V times cosine, the unit vector cosine theta comma sine theta. Okay. All right. Let's set it just right every way you can say it. Now let's get to example 6. Okay? Okay? Any question on that before I leave it? Need help there a little longer? Okay. Example 6. The vector V has a magnitude of 3. So I'm going to write it this way. Magnitude of V is equal to 3. It rhymes. Okay? And makes an angle of 30 degrees, which is pi 6, with the positive x-axis. Theta at 30 degrees, pi 6. That's approximately that. Yeah, but what you need?
I was wondering if you could sign off on my class. I'm going to try to take a physical science class this next
Second mini term?
Yes, sir, but it runs 15 or 20 minutes from my other class.
Right.
So I was wondering if you could sign off.
Oh, that'll be fine. Do I have to sign anything?
Yeah, I think so. I'll go get some for you.
Okay.
I'm sorry I didn't interrupt the class.
Yeah.
I couldn't find you.
Okay. Are you still going to be around? What time is it now? Wait. I haven't let you. We finish at 2 what? 2:10. So we finish about 10 minutes, 30 minutes.
Yes, sir. I'll be back.
Okay. You don't want to wait 30? You need to move.
Oh, no. I'm fine. 30 minutes is fine.
Okay. Yeah, why don't you come right then and I'll be able to do whatever then. Is that okay?
Yes, sir.
All right.
Thank you.
I just don't understand it. I just don't understand it. All right. So this is 30 degrees or pi 6 radians. Okay? Okay. Vector V has magnitude 3, makes an angle of 30 degrees or pi 6 with the positive x-axis. Write V as a linear combination of the unit vectors I and j. Okay? So, what will vector V, not magnitude, but vector V? Linear combination of I and j. It's going to be something, another I, plus or minus, I'll go on and put it, it's going to be plus something, another j. What goes in those places? Cosine pi 6 and sine pi 6. But I think we know what both of those are, don't we? What's cosine pi 6?
1/2.
No, that's the sine. Square root of 3 over 2. That's it right there. Now, another way you could write that, I don't think they want you to, but it would make great sense to me if you put 1/2 times root 3i plus j. Okay, that would be perfectly fine too. Now notice here, when we're writing like this, parentheses are fine when they are distributing, because ij, the vector parts of it are in the I and j, so you don't need vector brackets there. That would be mixing up notation. But I bet you that's how the book leaves it. And that is, oh, I forgot one big thing. That is not vector v, that would be the unit vector in the direction of vector v. Vector v has a magnitude of 3. So it would be 3 this and 3 that, which would be 3 root 3 over 2 and 3 halves, which would be 3 root 3, and this would be a 3. Okay. That's how they wanted it. The magnitude goes in front. And they told us that was magnitude of 3. Make sense? What you gave me was the unit vector in that direction. This has magnitude 3, so just multiply it by 3. All right, good deal.
I mean, it wouldn't be like proper to say 30 degrees instead of.
Yeah, it would be okay, because what you're doing is taking the sine and cosine of 30, and that's the same numbers, okay? So as long as you take it to the next step, it's fine. You can call it anything you want to in the intermediate, you know, but you ultimately to get to that. The book will use it mostly in radians, though. In calculus, you just always deal in radians because your rules, your formulas, and everything work so much better there. Well, let's see. Okay. Here, we've been at this slide before, but they had skipped 6, so let's come back to it. Vectors have many applications in physics and engineering. One example is force. Okay? Velocity is a vector, displacement is a vector, acceleration is a vector, force is a vector, momentum is a vector. There's tons of applications of vectors in physics and, of course, engineering. A vector can be used to represent force because force has both magnitude and the direction. Okay? 2 or more forces are acting on an object, then the resultant force on the object is the vector sum of those vector forces, not the scalar sum, the vector sum. Okay? And here is the example of that they give for this. 2 tugboats are pushing on an ocean liner, as shown in this figure. Each boat is exerting a force of 400 pounds. What is the resultant force on the ocean liner? Okay? Now, if you're wondering if this is at all reality, it really is. When great big ships pull into a very small port, which ocean liners do, and naval vessels do. I mean, most ports are somewhat restricted. You always have what they call a harbor pilot come out and actually takes control of the vehicle, of the vessel. You know, because they know the harbor, they know the issues, and they've been in there, they know winds, they know all sorts of things, and they actually guide you in. Even on naval vessels, the harbor pilot is on board once you get into what they call inland waters. It's certainly something as big and massive as a ocean liner, not an easy thing to get to maneuver. So they always come in, and they may be directing their tugs to get you where you need it to be. Okay? So this tug is coming in at an angle of 20 degrees with the horizontal here. So they name it a minus 20 here. By the way, that's also 20 degrees here if you think about alternate interior angles, they're the same. And this one's 20 degrees with the horizontal here, which would be the same as 20 degrees here. Now the difference here is they call this a minus 20 and this a plus 20, but it's the same type of deal. Now, this writing is a little bizarre here. You have to follow the braces they have here. The force here is 400, was it newtons or pounds? Pounds, 400 pounds, okay? 400 pounds pushing at an angle 20 degrees below the horizontal, okay? Which, if this was really a real life situation, what is horizontal? Horizontal is like this. This is like this, you know, so whatever. But anyway, 20 degrees there, and this one's 400-pound force pushing up this way. Well, let's break this down into components. The horizontal component of this is 400 times the cosine of minus 20. Now, anyone remember what cosine of minus 20 would be? Cosine it, not the number part, the sine part, S-I-G-N sign. All students take chemistry. Cosine is positive in the fourth quadrant. Okay, so this is the same as cosine of 20, by the way. Whereas this one, it is 400 times the cosine of 20. That would be this. That's the magnitude of the force times the angle. The vertical component would be 400 times the sine of minus 20, and the sine of minus 20 is minus sine 20. Remember, it's an odd function. But this one is 400 times the sine of 20. Okay? Well, then, guess what? These two are going to cancel out. Those forces are working against each other. So they're not contributing anything. So part of this 400 pounds of force is not going to push the boat, it's canceling the push on the other boat, you know. So those are unuseful forces. Okay? Now, if you could decrease the angle a little bit, you could get better force out of this, because you see the horizontal components add, because this is cosine of 20, because cosine is an even function, and this is that, so these two are adding, these two are negating each other. Okay? So the resultant force is the sum of those two horizontal forces, which is double any one of them, by the way. Okay? So you have to pull out your good old calculators and do that, and you see that it just comes out being that this thing is the same as that thing, so it's 800 times the cosine of 20. Put that what it is. Oh yeah, getting your calculator. Yes, 20 degrees, right? Be sure you're in degree mode.
Is 400 times cosine 20, sine 20.
No, you don't need the sine 20. Those are going to cancel out. So 400 or 800, whichever you choose to do. If you do 400 times the cosine of 20, now what are you doing? Are you doing the y's or are you doing the x's? It doesn't matter. You can do either one of them. Were you doing these first? Or were you doing these first?
I was doing what was on the paper here, F1, force 1, in the book.
Okay. Okay, well, there's not much you can do with that because those are in different directions. Those are not adding at all. This is just giving the vector. Go down to the bottom of that, you know, when it says F is equal F1 plus F2, and notice there you 400 cosine 20i, but you have another 420 cosine I, so that's 400 cosine 20i, I said on backwards, plus 400 cosine 20 degrees I, that gives you 800 cosine 20 degrees I. Whereas the vertical components, 400 sine 20 degrees I minus 400 sine 20 degrees I, that adds to 0. Okay. So just do the horizontal component there, 800 times the cosine of 20.
And I got 751.75.
Okay, they rounded to 752. This time they're rounding correctly. So these two components added together to 752 pounds. These two components, when added together, go to 0. But think of this. Your total force was 400 plus 400. That's 800. But you're only getting effectively 752 pounds in that direction. Why? Because part of the forces were working against each other and canceled each other out. But that's necessary. in order. You can't put them right next to each other because then they wouldn't have a flat surface to do them. See, this way they're pushing perpendicular to the hull of the ship. If you put them both this way, they would be right in the screws and at an angle, and it wouldn't work well.
And I mean, losing 48 pounds isn't that bad.
No, it's not bad at all. Okay, for that purpose. I give the example when I'm teaching physics. When we moved into our current house, it has lots of trees, and some of them very nice trees, but there were two scrawny little pine trees that had been trying to make their way through the oak canopy to get some sunlight. And they were really crooked and ugly trees. And there was also a little maple that was really bad looking too. I hated to cut maple, but we had to cut all three of them. Those pine trees were tall but very thin, and my father-in-law and my brother-in-law came down from Huntsville, and they were going to help us do that when we were moved in there. But the one pine tree was had a lot of potential to fall toward the house. We didn't want that to happen. So we got a rope and threw it up as high as we could, finally get one of the limbs way up there, because it went a long way up, got the rope to come down, and so my brother-in-law pulled on that way, and I pulled this way to get the tree to pull down. Now, we were defeating each other to some extent because our forces were like this, just like this was, and so the horizontal components added, but the vertical components canceled. So we'd have gotten more result if we'd have stood closer together, right? Why didn't we?
For more control?
Because then the tree would have fallen on both of us.
Oh, well, yeah, right.
Yeah, right? So we wanted to get some distance apart. We didn't mind losing that 48 pounds, fighting against each other rather than have the tree fall against us, fall on top of us. So yeah, there are reasons for that. And that was our reason.
Pretty solid.
Huh?
Pretty good reason.
Well, if you'd have been there, you'd have thought of it too. You wouldn't have been pulling right toward you. No, not a good idea. Okay. All right. So the resultant force, and notice they said most of the time the resultant force is less than the sum of the two magnitudes. And this is an example of that. All right. Now, let's see how they do the problem. Using figure 1112 that we just said, you can represent the forces exerted by the first and second tugboats. First tugboat, the force is 400 times the cosine of 20, comma, the sine of 20. Okay? Which one are they saying number one? Oh, they did the lower one number one. That's what I said. I thought the upper one was number one. I said one of those should be negative. Okay. And again, magnitude times the unit vector. That is the unit vector, cosine, sine, okay? And that would be cosine 400 cosine 20i plus 400 cosine sine j. Now this is one of the reasons that go from component notation to this, so you can not confuse what you're adding together. You can see these are the i's, those are the j's. Up there, it could be some places where you could trip yourself up. Okay, force 2, 400 times the cosine of negative 20, comma, sine negative 20. Okay? But because cosine is an even function, cosine negative 20 is the same as cosine 20. But because sine is an odd function, sine of negative 20 is minus 400 times is minus sine of 20. So when you multiply by 400, you get this. So when you go to linear combination form, so I'm not used to calling it that, then you get this. So when you add those two together, both tugs are pushing, so you're pushing these together. The first tug pushing with this one, second tug pushing with that one. Notice this and that are exactly equal but opposite, so they add to 0. You add the i's together, and you get 800 times the cosine of 20 degrees. That's what we were doing, the figuring then. And that gives you 752 degrees, pounds, approximately in the I direction. Okay, so the resultant force of the ocean liner is approximately 752 pounds in the direction of the positive x-axis. All right. In surveying and navigation, quite often they'll use the term of bearing, okay? Is a direction that measures the acute angle that a path or line of sight makes with a fixed north-south line, okay? So let's say this is north-south. It may not be, but it's approximate. North-south. This is north, that's south. Okay, there's the line. So you would be about 10 degrees west of north. Okay? This angle in the board here would be maybe 40 degrees east of north. That window there, the edge of it over here would be, we need an acute angle, so I'm not going to go from north, I'm going to go from south. That would be about 50 degrees east of south. Okay? And the edge of the, let's do this edge of the chalkboard here, that would be maybe 35 degrees. Set it back. That was west to south. This is east to south. Okay. Turn it around. Okay. So, those are what we mean by bearings. From either north or south, what acute angle to the east or to the west. In air navigation, bearings are measured in degrees clockwise from north. Clockwise from north. So if we were flying northward, or pointing, well, our compass is north, let's say that, and we're flying in this direction, that would be 40 degrees east of north, okay? And we just call that 40 degrees, okay? Over here would be 160 degrees. Over here would be 300 degrees. Up there would be 290 degrees, 270 degrees, and that would be 315 degrees or something like that. So it's just measured degrees, but that's clockwise, not counterclockwise. That's why pilots, no, I won't get into pilots, okay. Oh, that's the last slide. They don't even do the example. So let's go back and do the example. I think. Okay. And by the way, this example, you can see larsoncalculus.com for an interactive version of this type of example. So they don't have it on the slide set, you can find it there. Okay, an airplane is traveling at a fixed altitude with negligible wind factor. Good. The airplane is traveling at a speed of 500 miles per hour with a bearing of 330 degrees. So if this is north, the bearing of 330 degrees is going to be over here somewhere, which is 30 degrees short of being due north. Okay? And the speed is 500 miles per hour. Okay? Bearing of 330. So the theta here is 330 degrees. And by the way, they always use degrees, as shown in this figure. Okay? Okay. As the airplane reaches a certain point, it encounters a wind with a velocity of 70 miles per hour in the direction north 45 east. They're changing all sorts of, but it happens to be the same. So the wind is north 45 east, something about like this. This is the plane. Let me draw my little ugly rendition of a plane here. That's the plane. This is the wind. And the wind has a magnitude of 70 miles per hour. Okay. In the direction of that. What are the resultant speed and direction of the airplane? So he thinks he's flying this way, but the wind's pushing him this way. So we have to figure out what his resultant speed and direction is. Well, we need to come up with vectors. Okay? Now, there's several ways you can do this. The book does it one way. I'm going to do it slightly differently. We said this was 330 this way, so we're 30 degrees short of being due north. So he has a northward component. Let's do it this way. His northward component, and he has a westward component. The westward component is the sine of 30 degrees, which is 250 miles, because the sine of 30 is 1/2 miles per hour. That puts his northward component here to be square root of 3 over 2 times 500 miles per hour. I'll take the 2 into the 500 and make it 250. So someone's got to calculate root 3 times 250. Say that again.
433.01.
Okay. So that is his velocity in the northern direction. Okay? Velocity in the western direction was 250. Okay. Now, the wind speed, this is 45 degrees here, wasn't it? Okay. So that's going to be root 2 over 2, and this will be root 2 over 2. Okay? So the northern component of that would be, so it's 70 miles per hour times root 2 over 2. Well, let's make that 35 times root 2. No, root 2 is 1.414. 35 times root 2.
35 times square root of 2 equals
Wait. Say that again. What you did?
35 times the square root of 2.
35 times the square root of 2, yeah.
49.49.
Yeah, 40. I thought you said 29. Okay, I'm sorry. So this is 40. Say again.
49.5 is
49.5. Did you round to get that, or was it 0.4 something?
0.4974.
Let's call it 50. Okay. We'll just call it 50, and this will be 50. Okay? Approximately. Okay? So, what would be the overall? This is 200 in this direction. Okay, because you subtract the 50 from that. And here these two are in the same direction. So this was 433 plus 50. Isn't that what we said? So this would be 483 in this direction. Okay, so that would be this way. So what the resultant speed would be the square root of 483 squared plus 200 squared, which would be 440,000. You don't have to square it, but if you want to, you could. And these are plus. Do that. 483 squared plus 40,000. Take the square root of that.
$522.77.
523 then?
Right.
523, approximately. That would be his approximate speed. What was I put in there? Miles per hour. Okay? Okay. Now, let's see what they got.
If they rounded wrong,
They said 522.5, and we did 523. That's the same.
Well, I said they rounded wrong, because ours was 522.77.
Yeah, well, I also adjusted that a little bit. You said 49 point something. I was just rounding it, and we came out close enough. Okay? So that's but we still don't have the angle. That's our effective speed. What did they call it? Resultant speed. What is the direction? Well, the direction is we had 200 miles per hour to the left, to the west, and 483 to the north. So we need to do the tangent of that angle. But which way are we going now? Yeah, they're going back to their thing. So this now, whereas before this was, I wrote it down somewhere, 330. Now it's going to be, I don't believe it. No, they're not doing this right. Goodness, what are they doing? Where did they get 112? I see. They're doing their angle this way. Okay. Now that makes sense. They're not doing it from north. They're doing it from back to due east again, which is not the way they do things here, but that's all right. And it has, the wind has pushed the plane a little bit this way. Okay. So it'll be a little bit less than the 120 it was. That's what they went back to do. Goodness gracious. Okay. What I would have done here is your northward component was 483, the westward component was 200. So that would have been the tangent of theta would have been, I think the north, 483 divided by 200. Okay. So, are we out of time?
Yes, sir. I have to go to work.
Yeah. Okay. If someone got a calculator out, you don't have to. If you need to go, you can. Okay. Do 483 divided by 200, and then do the arctangent of that. Second? Oh.
$67.5.
Yeah, same thing.
Okay. Do it the other way. 200 divided by 483. And do the arctangent of that.
$22.489.
Okay. They were doing basically 22.6, so we were pretty close. That's how many degrees past what they're calling 90 degrees. So, yeah. That's actually reverse these two. You got it. All right, homework exercises here. I'll put them on YouTube. You can listen to them. Do either 5 or 7. They're both at Calc Chat. 5's at Calc View. Oh, do number 3. It's at Calc Chat. Do any of the odds 9 through 15. They're all at Calc Chat. 11's at Calc View. Do 17. It's at Calc Chat. Any of the odds 19 to 23. They're all at Calc Chat. 21's at Calc View. Do 25. It's at Calc Chat. 27. It's both at Calc Chat and Calc View. Any of the odds 29 to 33. They're both at Calc Chat. 31. They're all at Calc Chat. 35 or 37, they're both a calc chat. 35 is a calc view. Any of the odds, 39, either 39 or 41, they're both a calc chat. 43 is a calc chat. Any of the odds, 45 to 47, or 45 or 47, they're both a calc chat. 47 is a calc view. 49 or 51, they're both a calc chat. 49 is a calc view. 53 or 55, both a calc chat. 57 or 59, if you want to, you can try those there at calc chat. Any of the odds, 61 to 65, they're both at calc chat, all at calc chat. 67 to 71, they're all at calc chat. 73 is a calc chat. 75, you do any of the odds you want, 75 through 83. They're all at calc chat. And then do some true false, 85 to 93, they're at calc chat. 95 is a proof. If you want to do that, you can. It should be at calc chat. 97 and 99, you can do either of those. They're at calc chat. We'll start next time at 11:02.
All right, sir. Have a good one.
You too, thanks. Good
That
deal.
was the first test.
Yeah.
We're not on the second one, right?
No, that'll be
this
easy
one,
one.
right? I'm so I'll be in in class tomorrow, but for Monday next week, I'm Friday. I'm heading to Nebraska.
Oh, really?
Yeah, to go visit a buddy of mine in the military. And
Is that Air Force?
Yeah, he's in the Air Force, and I'll be back on Monday. I'll be coming back on Monday, so I'll miss class on Monday, but I'll be back on Tuesday.
Okay, good deal. All right, well, have a good, safe trip.
Thank you. And then I have the other